So we have one receding outflow at a fast velocity, one approaching outflow, and you see that actually the outflow is not going along this direction, where it can be seen that there is some kind of outflow, but it's actually going along this direction. So really the fast outflow here is along this direction, not that one. We also see that there are two components from the shell, the one which is approaching us and receding. And then at the innermost region here, we see that there is a kind of low velocity toroidal-like component, which is embedded within the nebula. One interesting thing is that we have not only made this analysis with the nitrogen-2 line, but also with the recombination carbon-2 line. And when we use the recombination carbon-2 line, actually we see that there is like a kind of innermost shell there, which has smaller velocities than the outermost regions, and which is more compact. So here you can see the different components overplot on the image. So you see the outflow going along this direction. You see the shell there and this kind of toroidal components. And when you look at the carbon-2 line, it's embedded in there. So our next step is going to be obtaining also this kind of observation for the oxygen-2 and nitrogen-2 recombination lines in the blue, and then look at the carbon, nitrogen, and oxygen abundances of this PN to see whether the carbon, nitrogen, and oxygen ratios are consistent with a very late thermal pulse or a late thermal pulse. There is more coming. Jacqueline has found one object, which is this one, where we have one of the fastest outflows in a PN. So this is like a position velocity diagram derived from the MEGARA observation, and we see that there is one component here and another there. So probably if we made a correction for inclination effects, those outflows are moving at velocities larger than 300 or 400 kilometers per second. And then I moved to my baby, NGC 2392, the Kimono Nebula, and which is very peculiar. This was actually the very first PN with a fast outflow. In 1985, Giskin and collaborator described a jet-like multi-node bipolar mass flow with a velocity of nearly 200 kilometers per second. That was the very first on a PN. So here, this is the shell observation, and you can see the nitrogen-2 lines, the alpha line, and you see this component here and there that move at very fast speed. And this is an outflow which is going along approximately this direction. So this is a very peculiar PN. The inner shell is expanding at 90 kilometers per second, which is very unusual for a planetary nebula, for the inner shell of a planetary nebula. You find these velocities in bipolar PN, but never in a shell of a PN. And in addition, the central star is too wimpy. It does not have the UV flux or the temperature to produce the large amount of helium-2 emission seen there. As a result, the effective temperature as determined from non-LT models, and this that correspond to Sanstra models, is completely discrepant. It's much, much higher for the Sanstra temperature. And also, if we look at the X-ray emission, okay, so this is the X-ray emission here from the diffuse emission inside the inner shell. It has an X-ray temperature that cannot be produced by the stellar wind of the central star. The stellar wind is too slow. It has a velocity of 300 kilometers per second, which cannot produce, even in the case of an adiabatic shock, which is the most efficient that we can imagine, it cannot produce the plasma temperature which is in there. In addition, we see that the emission from the central star, so this is the emission from the central star here, multiplied by 10, is this blue, but multiplied by 10. And we see that this is really peaking at 0.9 kiloelectron volt with a tail that extends down to 3 kiloelectron volts. This is unseen in any central star of planetary nebula. So there is something going on there. And actually, there are many authors, and I'm among them, that we believe that this is really a post-common envelope double degeneracy binary. So this is the central star of the PN, which is now evolving into the white dwarf phase. And there is an unseen, very small, very compact white dwarf star with probably a temperature of 200,000 Kelvin, which is really providing the ionizing power to this source. Because we see also next ray modulation, probably there is some kind of accretion onto an accretion disk. At this moment, there are different periods depending on the lines that you see on the spectrum of the star, and also the X-ray modulation. So the period of this binary system is really quite unknown, but there is something there going on there. Now we can tell if there is a star which is still accretive material, is going the jet to be still collimated? Actually, when we look at position velocity maps, here we see that the jet actually goes down all the way to the continuum of the star. So it seems that the jet is emanating from the central star at this moment. And that would make an active jet in a post-common envelope PN, which would be the only one. But when we try to see the jet in direct images, see this is the nitrogen 2 position velocity diagram. You see the jet here very nicely. But because the nebular shell is very bright, when you go to images, you don't see the jet here. There is, and also there is a lot of structure, emission components there, so it's not possible to find where the jet is. Some authors have made some isovelocity images using many long slits, and then making interpolation between what we see in the shell observation with those long slits. So in particular, Bruce Balick in 1987, they found some emission here in the most extreme isovelocity channels that could be associated with the jet. But it was difficult from there to derive what's the exact morphology of the jet. More recently, Maria Teresa Garcia Diaz also made observation in a lot of long slits there, and she produces some maps of the jet. So actually the jet seems to be not really full collimated, but it has some structure. So with this idea in mind, we have obtained, I think it's 15 observations of the schema, because the schema is much larger than the field of view of MEGARA. We mapped it, we made a mosaic, and actually in 15 of these fields, we were detecting the jet. So the jet is detected in thousands of spaxels. And we can really resolve, because the high velocity of the jet, we can resolve the jet from the nebular emission. And this is shown here. So we have the jet in this particular case, in this particular region, it's to the red, and we can make an image of the jet. And here, this is the emission from the nebula at mostly systemic velocities, and then we have a different image here. So playing this game for the whole field of view, we have made these maps of the emission of the jet in the schema. So here we have the flux and velocity dispersion in the nitrogen 2 line. And we also have the flux in the sulfur 2 lines and the density. For the H alpha, we could produce these maps also for what we call the mid jet and the outer jet, but actually for the inner jet, which is projected against the bright nebular shell, which has also a fast expansion, we could not resolve the H alpha from this line. So we stopped. We didn't try to make a full map of the H alpha. So how does the jet compare with the nebula? Well, first thing is that we see that the jet really emanates from the central star. It goes across the inner shell and it gets outside the inner shell. So it's really going across the edge of the inner shell. And when we compare it with the outer nebula, then we see that the jet actually, it has some kind of like precession-like motion there, and it even extends outside the nebula. So here and there it's projected against the nebula, but we see clearly here and there that it goes beyond the limits of the nebula. So there is no really connection between the jet and the nebula. So using the spatial kinematical property, I see that we could not see the jet, but now that we have this map of the jet, we could actually see that there was something. If we look at the sulfur 2 images, there was something, some emission there, and maybe some ratio of nitrogen 2 to oxygen 3. So we see that the jet is there, but actually without the evidence of this spatial kinematically resolved jet, it could have been impossible to really say that this is the jet in the schema. So these properties that they look like those of precession jet, we have modeled this using a very simple model, like a toy with a precession jet there. And actually they fit very well what we are observing. So we see that the jet is really wobbling here. And when we look at the position velocity map, we see here that our best fit model is here in black. And those are like different models with different parameters. So in order to determine what are the uncertainties. So with this information, we have been able to derive the properties of the jet. For instance, we know now that the precession jet is something like 3,000 GR. The inclination of the precession angle is 33 degrees. The full linear size of the jet is it's more than 2 times larger than the diameter of the inner shell there. And it's older. So the jet was emitted before the nebula was created. Also, we see that there are some discrepancies as for the mass loss rate or accretion rate. So again, the central star cannot provide the mass to produce the jet. So there is something on additionally going there. And there is some evidence that maybe the fast stellar wind from the central star is not isotropic, but it could be something like to have some preferential direction, like a bipolar outflow that actually could be even the very beginning, the onset of the jet emerging from the central star, what has been actually detected. When we compare the jet in the Kimono Nebula with those on post-common envelope PN jets, we see here in most of the cases, for instance, this one, the necklace, we see that the jet is here and there. So there is no connection between the jet and the central star. And this is also happening here in all the sources. And also for Fleming 1, for instance, the jet goes down there and then there, but there is no connection. So this is actually the post-common envelope jet in the schema is the only one where the jet is at this moment being collimated and launched. Of course, we know that this is something that happens for AGB stars, like this one, post-AGB star, or very young planetary nebula. So those are still able to collimate the jet because probably the mass loss rate from the AGB phase is large enough to accrete enough material to produce the jet. But this is not the case for those post-common envelope jets. There are many similarities between the jet of the schema and that one of Fleming 1. So we see, for instance, that in the case of Fleming 1, there is an envelope that we see projected on the sky, but in the case of the Eskimo, it's probably like face on. It's like we see like a pole on view of the envelope. There is like a low ionization features in the Fleming 1 that we see clearly that this is a kind of ruin-like structure that we see on projection on the sky on the Eskimo. So one can see here the model that made Maria Teresa Garcia Diaz of this source that actually correspond quite nicely to what can be seen here in this other case. So we are kind of launching the idea of proposing that Fleming 1 and NGC 2392 are very similar sources, but seen from different point of views. And also, in the case of Fleming 1, this is like a bit later when we are observing this source, because the outflow is not being collimated at this moment, but it is in the case of the schema. So we published these results very recently in the Astrophysical Journal. So we also conclude here that the case for a launching of the jet at this moment is also telling us that there is a double degenerate system which is undergoing accretion. And just to conclude, some very basic ideas that high dispersion integral field spectroscopic observations of planetary nebula help us a lot to determine what's the physical structure of the PN, to see what are the different components, the inclination of the system. And this is particularly interesting in the case of compact PN, where different components are merged because we don't have the spatial resolution, but the spatial and velocity resolution are going to help us to distinguish these different components. It could also be used to see outflows that they are projected against very bright nebular shells. And as in the case of HUBI1, if you really want to determine the properties, the physical properties, the physical conditions, excitation, extinction, and chemical abundances of weak, of faint clumps of material embedded within the shell, you really need to go to this kind of observation to separate spatiokinematically these components, this weak component from the bright nebular shell. So I think that there is a lot that can be made with this kind of observation that we are applying to planetary nebula. And we are also now moving to nova shells, to nova remnants, because they also have very high velocities, and we can see the different components of those shells. Thank you very much. Now I'm happy to take any questions.
Yeah, thank you, Martin. And let's try the new system of asking questions here live or remotely. So please, if you have a question, raise your real hand here. Remote hand there. You have the mobile with the application on the back.
No. I didn't know how to do that. I just did that from struggle.
Renee's mobile.
Okay. Thank you very much. It's just, I mean, just to know what is the spatial resolution that you have in your images with MEGARA?
Well, you know that the MEGARA field of view is small. It's something like 12 by 11 arc seconds. The X-axis is 0.6, so you are going really to depend on, it's going to be a convolution between the scene that you have and the size of the spaxel. We are typically applying for those sources for seeing below 1 arc second. And in these cases, we have made some measurements of the full width and maximum of stars in the field of view, and we can say that we have something like 1 arc second, 1.1, 1.2, up to most.
Yeah, because it's good that you can resolve in velocity when you have high dispersion, but it may also help to have higher spatial resolution. So do you have any plans of improving your information, I mean, observational information by asking for data coming from places where the spatial resolution is expected to be higher?
Yeah, indeed, we have a project. Let me see too. Actually, Sarah and I had applied for Muse observation of Fleming 1, because now we have too many details of the Kimono Nebula and properties of the mass, period, age. But as for Fleming 1, because it's very large and it's difficult to trace with just a long slit, there is a very few observations. There is one thing which is very important. When you make observation with long slit, with the shell, it's almost impossible to get the flux calibration properly. But when you're using this kind of observation, that's very straightforward. And Fleming 1 actually fits very nicely in several Muse fields. And also Muse does not have the spectral resolution of MEGARA. In this case, we are talking about a jet which is been moving at 100 kilometers per second with respect to the nebula. So in this case, we are sacrificing a bit the spectral information, but we are getting much better spatial information. So we hope to be able to produce the same kind of models for this source as we have for the Eskimo.
Okay, good. Thank you.
Well, welcome.
So we have another question here, Pedro. Go on.
Hello, can you hear me?
Yes.
Good. Thanks, Martin, for a nice talk that I have enjoyed. I always enjoy these talks that you guys give because of the very nice pictures I can always see in them. I have a couple of related questions. I want to start asking you about these late thermal pulses or very late thermal pulses that happen in these stars. I understand that they do not occur in all stars, all post-AGB stars. I don't know, maybe in a fraction of them. What drives these events in these stars that is not there in the other stars that don't have them?
So the very last, Pedro is asking whether those very late thermal pulses are going to happen in all, let's say, post-AGB stars or only in a fraction of post-AGB stars, and if so, what's really driving this event? So when the star leaves the AGB, it's going to be basically a core of carbon and oxygen. And then there is going to be a layer of helium, and on top of that is going to be another layer of hydrogen. So in this horizontal region of the Hertzsprung-Russell diagram that the star is crossing during the PM phase, the star is burning hydrogen on the top of the surface layer, and this hydrogen is going to produce an increase of the mass of the helium layer. So in most of the cases, the helium layer is going to be have a small mass and nothing is going to happen. Let's say for maybe 80% of the post-AGB stars, nothing is going to happen. But for some 20 of them, the initial mass of the helium layer is close to the critical mass. When this critical mass is reached, because the helium on top of them is producing more helium, then the helium is going to ignite and it's going to produce this thermal pulse. So it may happen at the very end of the AGB phase, what's called a final thermal pulse, and then the PN is ejected during this final thermal pulse. It may happen while the star is on this horizontal track, and this is called a late thermal pulse. And it may happen when the star has already begin to cool down the cooling track. And this is a very late thermal pulse. We consider that this is what actually produces all the Wolf-Rayet type central star of planetary nebulae. So those are central stars whose atmosphere are basically depleted of hydrogen. And so they have a spectrum which is similar to those of Wolf-Rayet massive stars. Those are about 15% of the central star of planetary nebula. So that's why I'm saying that maybe something like 20% are the stars that they are going to suffer, to experience this late or very late thermal pulse to become born again planetary nebula. But this is a very short transitional phase. It's going to last for a few hundred years, and it's going to depend on whether the outer nebula is it's very tenuous, it's very old, then you are going to be able to identify very clearly the signature of a boson again event. But if it happened while the nebula is compact and dense, and then it's difficult, it's quite difficult to identify that there is an inclusion of hydrogen deficient material there. So that's something actually that this kind of observation can help us to distinguish. And we have a sample of sources selected from their infrared properties that are very good candidates to have experienced this kind of events.
Yeah. So just to finish with my questions, once this event happens, from your answer, I take that there is no way of differentiating between one of these stars as a white dwarf that has not gone through this event from one that is coming from the born again phase and coming back to the white dwarf stage. Is that correct?
No, actually it's not. When this event happened, the chemical composition of the surface of the star goes from hydrogen rich or helium rich to carbon and oxygen rich. So there is a variation, and then we have these two different kind of central star with some objects in between there. But actually, we consider that this is something that really changes dramatically the chemical composition on the surface of the star.
Surface, okay. Okay, thanks, Martin.
Welcome.
We have some problems. The people online, they cannot hear the questions.
Cannot hear the question. Okay, I
did it. Marisa Vargas say that MEGARA, she didn't catch the convolution. In MEGARA, the spectral resolution is 100%. Sorry, it is moving. It's 100% guaranteed and constant at as the slit is at the exit of each fiber. So that the spectral and spatial full width maximum is guaranteed. A different thing is the flux calibration, where you will have to add RGB spaxes and take into consideration the scene. This is the question or comment.
So she's implying that you can make some kind of the convolution of the images to, because it wasn't clear to me what she was asking.
Hello, can I say?
Yes, please. Hello.
Hello, Martin. Thank you very much for the talk. No, it was just a comment because I didn't hear the question. I don't know from whom, about convolution and about the spectral resolution. And the point is that with MEGARA, you don't have the problem of convolving with scene, because the spectral resolution you get is exactly the same, whatever the scene is. Another thing is how much flux you have in each fiber. So in that regard, you have to take into account the spaxel on the overall image on the eye view. But for the spectral resolution, this is a great advantage of fibers, that it is always the same, so you are not losing the details.
I quite agree. I don't know whether I was clear before, but basically the spectral resolution, it's excellent, and it doesn't not we haven't seen that it changed across the field of view, so it provides us with a very nice piece of a tool to work. As for the spatial resolution, well, because the spaxel size is quite similar to the scene that we are requesting, so actually there is some convolution between the size of the spaxel and the scene. But basically, what we see in our images is the original scene. It just degraded by a few %, so there is no major issue on this. We are close to the Nyquist criterion for this, as for the spatial resolution.
So I have a question about Mayra, but I don't know if it's answered.
Hi, Martin. Thank you very much for this nice talk. I had a question regarding the planetary nebula M2 and 31. You mentioned that you have detected an outflow asteroid component with MEGARA. I wonder if you had plans to confirm or to see these components also in radio. Do you plan to propose a radio observation with large interferometers to see these components associated with this nebula?
Well, that could be interesting. At this moment, I don't have this in mind, but because okay. Okay, sorry. So Mayra was asking whether the collimated outflow and the toroidal component that we see in M2-31 that we see in the optical, if we have in mind to propose a radio observation, and more precisely radio interferometric observation to see those. Well, at this moment, we are quite busy with some radio interferometric observation of a born again PN, Abel 58. Well, this is a very good idea, but we need manpower basically to do that. But it could be interesting to see those bipolar outflows that they are. My impression is that because those are compact sources, those are also young sources. And so in this case, we are really seeing the early collimation of the outflow when the density is going to be high enough, and maybe there is some, who knows, synchrotron emission or radio emission from free electrons. So that could be something interesting. And I should ask Jesus Tola, who is leading this line, to propose this observation. Thank you for the idea.
I only want to comment that there is a lot of pressure to get time with ALMA.
Yeah, I know. So she's saying that there is a lot of pressure to get time with
but
ALMA.
We can propose with NOEMA or with the 2mm array, which is is easier to get.
Okay, let's think about it, and we can see whether there is anything on the archives to see whether there is radio emission, and based on this, we can make some proposal. Good, excellent.
Pedro? Go on.
Yes, okay. Thanks. Sorry, if someone else asks a question, I can wait. Otherwise, I can go with my last question. Martin, well, we all know that recently a Jupiter-sized planet has been detected around the white dwarf, so we are just starting to confirm that the planet survived the last stages of stellar evolution. I hope we can have to do a say on this soon. So I understand that if a planet orbiting far from the star is finding a denser environment when it is embedded in the in the ejecta, in the ejected envelope of the star, it may migrate inwards or outwards. So does the presence of a long period planet, giant planet, can it have an effect on the building of structures in planetary nebulae?
Pedro is asking me that because there has been the recent detection of a Jupiter-like planet around a white dwarf, so that there is evidence that the planetary systems are going to survive the AGB and planetary nebula phase. Because depending on the evolution, planets are going to migrate either inwards or outwards. He's asking me whether those planets are expected to become a piece of for the building of the planetary nebula, for building of those structure. And actually, there is a lot of work on this respect from the a theoretical point of view. There is a lot of simulation trying to find what are the, let's say, the small size of the body around an AGB star, which is going to change the velocity field the mass loss so as to produce some kind of, for instance, equatorial enhancement of density, or some kind of bipolar outflow so as to produce the shaping of the planetary nebula. And indeed, it seems that depending on the properties, that maybe a Jupiter-like planet at the right position from the AGB star is going to be able to produce mild effects on the symmetry of the outcoming planetary nebula.
Thanks, Martin.
Mm-hmm. Thank you, Pedro.
Okay. If there is no more questions, I really apologize for these technical problems. We need to improve some stuff, and I think in the next seminar we can do it better. Thank you, Martin, for this talk, and thank you all for this presentation. I think Pepe just want to say something.
Oh no, just thanks.
Thank you, Pepe.
Thank you very much. Great talk.
Yeah, actually, I think that it's really very amazing, to be here with people around, to be able to see the faces, but also to be on broadcast through Zoom, so that you know that we have a larger audience. And thank you very much, René, for the.
And thank you to René also for this experiment.
Thank you.
Yeah.
Thank you very much.
Okay.
¿Sobrevivimos?
Sí. ¿Y están escuchando? ¿Y las preguntas? Entonces no entiendo por qué.